Okay. So today what we're doing is we're going to be drawing on a lot of relationships that we've looked at. So we're looking at the function, okay, its first derivative, which tells us the slope, turning points, and then its second derivative, which tells us points of inflection. So we've got a table right at the top of the page, and this is very important. This is a very important table. It summarises all of the things that are going to appear for us. And what we're going to do today is we're going to, if you look at our notes there, that's all of the questions from the textbook. Okay, it's a very short exercise in the textbook. So we're doing the textbook exercise together. And then I'm going to give you this supplementary resource. So this is a resource that I've produced over the past few years called Graphing Relationships Between the Functions. And this is a collection of exam questions with this skill. This is a skill that always pops up in exams, okay? And there will be one of these coming up in the test. So we'll hand that out when we get to it, but we're just going to go through all the textbook questions together. So here we have a quadratic, okay, we can recognise the shape of it, and we are asked to draw, using the graph, sketch graphs of f dash of x and f dash dash of x, okay? So I want to use this to sketch a graph of the derivative function. So the first thing we're going to try and do is draw a sign diagram of the derivative function. So we'll bring up a sign diagram here. And remember, the first derivative, all it tells you is when is the function increasing, when is the function decreasing. So that's what we're looking at. And we can see if you're walking along this function, you would be decreasing until you get to this point. Now, because it's a quadratic, this occurs exactly halfway between the two roots. So that's going to have an x value of positive 1. So we would be decreasing until we got to x is positive 1. So we have a negative slope, and then we would have a positive slope after that. So we're asked to draw a graph then that has these properties. Okay, so here's my Cartesian plane, and so it crosses at 1, that's where the root is, and it goes from below to above. Okay. Similarly, we know if this is a quadratic, then the derivative function will be the equation of a line. All right. So this is a graph of the first derivative. Next, we're going to draw a graph of the second derivative. So in order to draw the sign diagram of the second derivative, here's the sign diagram of the first derivative. Let's draw the sign diagram of the second derivative. We're going to go, all right, where do the points of inflection occur? Now, points of inflection occur when it changes shape, and it doesn't change shape anywhere. This function is concave up for all values of x. So let's look at our table and let's see how we could use that. If it's concave up, all right, I'm looking in the second to last row of the table. This means the second derivative is positive. All right, so that means the sign diagram of my second derivative looks like this. Which means when I graph it, it's going to be a horizontal line like this. Okay, and I'll explain the reasoning behind it for you. Our original function was a quadratic, all right? That's of the form x squared. When we differentiate that, we get a line, which is 2x. And when we differentiate 2x, we would get y equals 2. Okay, we have the equation of a horizontal line, y equals 2. So that's going to be the graph of the derivative. All right, I'm going to rub these two out so I can fit the next one in. Question B. So we need to draw a graph of the derivative and the second derivative. So I think the best thing for us to do is draw a sign diagram of the first derivative. So we're going to talk about where is it increasing, where is it decreasing. That's what the first derivative tells us. It tells us when we have positive slope, when we have negative slope. We can see we would be increasing until we get to -1. So we have positive slope until we get to -1. Then we would have negative slope until we get to here, which is +1. And then we would have positive slope after that. The sign diagram of the first derivative is just an indication of when is the slope positive, when is the slope negative. All right, and I'll put that one here. This one right there. So if I'm going to graph that function, okay, it has roots at -1 and +1. And it goes from above to below to above. Okay, so all I'm doing is taking that sign diagram and drawing a graph that has those properties. That is above, below, and then above. And similarly, I know with the nature of functions, this is a cubic, okay, it's got 3 roots. When I differentiate a cubic, I get a quadratic, okay? So what we expect. Excellent. Okay, let's move on to the second derivative then. So for the second derivative, we're going, where are the points of inflection? That's what we're asking. When is it concave up? When is it concave down? Now and with these questions, we're just sort of estimating. We're not told where they are. If we want you to be precise, we'll tell you exactly where they are. We can see this is concave down, and then somewhere around here it changes to concave up. It's opening upwards there, opening downwards here. So we'll call point O, or point of origin, that's going to be where the point of inflection occurs. It transitions from being concave down to concave up. Now, because it's concave down, that means the second derivative is negative. Okay, that's listed in the table. All right, it's the third row from the bottom. F dash dash of x is less than 0. It's concave down, and when it's concave up, the second derivative is positive. So if we're going to graph that function, okay, it goes through 0 and it goes from below to above. And similarly, we know cubic goes to quadratic, quadratic goes to equation of a line. Now there's one more important connection that we need to make, and this is one that I just really need to hit hard, okay, because this is the tricky one to see, and it's the very bottom row of our table. The points of inflection on f of x, okay, points of inflection on f of x, that's this one here, are the stationary points on f dash of x, okay, stationary point, local minimum, which is the roots on the second derivative. Okay, so you can see point of inflection on the first function corresponds with stationary point on the second function, corresponds with root on the third function. Okay, very good. Let's jump up here. So, pretty similar question at this one. We do have a cubic, it's got 3 roots. It's the first root, and this one is a double root. And so what we can see is we're increasing until we get to here, and I'm going to define these. If it's unclear, you get to choose. All right, that's going to be x is 1, and so it's going to be the first derivative. We're going to have positive slope until we get to x is 1. Then we'll have negative slope until we get to x is 3. And then we'll have positive slope after x is 3. So increasing, okay, the first derivative is positive. Decreasing, the first derivative is negative. And then increasing, positive. Now, the sign diagram is not something you have to draw, but it's something I'm going to encourage you to do because it's going to help you generate the graph for the first derivative function. So the graph for the first derivative function then just has these properties. Has a root at 1 and a root at 3, and it goes from above to below to above. Okay? Positive, negative, positive. All right, again, cubic, differentiate it, goes to a quadratic. All right. For the second derivative, let's draw its sign diagram. Okay, we have a point of inflection occurring on this graph. It changes from concave down to concave up, and it's around there somewhere between 1 and 3. We'll say x is 2. And the function is concave down. Okay, it's opening downwards until we get to 2. And after 2, it's opening upwards. So the graph of the second derivative then is the equation of a line, comes from below to above. All right, let's emphasize that last point on the table. Points of inflection on the function correspond with turning points on the derivative function, okay? Here we've got x is 2. The turning point on the derivative, x is 2, corresponds with roots on the second derivative. I'll make that very clear, that's the second derivative graph. Point of inflection corresponds with stationary point, corresponds with root. Okay, last one. All right, so we've got a bit more going on here. I'll say a quartic, because we have a cut, so we've got 2 roots and then a double root, so it's going to be a quartic. So let's draw the sign diagram of the derivative function. Okay, all you're asked, when is it increasing, when is it decreasing? So we could see we're going to be decreasing, you'd be walking downhill until you get to x is 0. We have negative slope until we get to x is 0. Then we have positive slope until we get to x is 2. Then we have negative slope until we get to halfway between those, which would be 3. And then after 3, so we'd be walking downhill, uphill, downhill between 2 and 3, and then uphill after 3. Okay, so if we're going to draw a graph with those properties, what we do is we mark the roots. All right, there's a root at 0, there's a root at 2, and there's a root at 3. And it goes from below to above, to below to above. I'll label those points. So that's 0, that's 2, and that's 3. This is the graph of the first derivative. Okay, let's draw the sign diagram of the second derivative. So, what we can see now, we can refer to this function. Let's do both. I want to point something out here. So, if we're drawing the sign diagram of the second derivative, our question is, when is it increasing? When is it concave up? When is it concave down? We're concave up until we get to here, where it changes to be concave down. It's concave down there until it gets to here, and then it's concave up again. All right? So we've got to approximate those points. This point will be x is 1. All right? So it's concave up until we get to x is 1. It's concave down from x is 1 to x is 2.5. And then after x is 2.5, it is concave up, opening upwards. So we can get it from the concavity of the function, but we sketch the first derivative, right? Just consider, okay, look closely here. If you just consider this function, okay, f dash of x, this is the derivative of this function, which means this tells you the slope of this function. Look at this. Positive slope until it gets to 1. Positive slope until it gets to 1. Negative slope until it gets to 2.5, halfway between 2 and 3. And then positive slope after 2.5. So we can observe that from the concavity of the original function, or even from when the first derivative has positive slope and negative slope. You can get it from either of them, just pointing out a connection. Okay, so let's graph let's graph the graph of the second derivative. So we have roots at 1 and 2.5, above, below, above. 1 and 2.5, second derivative, f dash dash of x. All right. Points of inflection on the original function, here they are, correspond with turning points. Okay, point of inflection here, turning point, root. Point of inflection, turning point, root. Okay, so that will always be the case for all functions. All right, so we do have 2 more examples there. I think let's go through them towards the end of the lesson. What I'm going to do instead, I'm going to pass out these booklets